Good morning, champs. A closed container with water can create a vacuum just by cooling. That sounds strange at first, but it becomes very clear once we understand one important thermodynamic diagram. Let's start with something familiar: boiling water. When water boils, it is no longer just liquid. At that point, liquid water and water vapor exist together. And that exact situation is the key idea for this video. Now let's translate that into a PV diagram. On the horizontal axis, we have volume. On the vertical axis, we have pressure. For a substance like water, the diagram contains a dome-shaped region. This dome is the most important new feature. On the left side, the substance is liquid. On the right side, we have vapor. Inside the dome, we have liquid and vapor together. So the middle region is the one we care about. It represents a two-phase state, part liquid, part vapor. Now here comes the one idea you really need to remember. Inside this liquid-vapor region, pressure and temperature are locked together. That means if I know the temperature, then the pressure is already fixed. And if I know the pressure, then the temperature is already fixed. So inside the dome, we do not choose pressure and temperature independently. This is the big difference compared with the ideal gas problems we solved before. There, we often use the ideal gas law to connect pressure, volume, and temperature. But here, inside the dome, that is not the right approach. Why? Because the substance is not just a gas. It is a mixture of liquid and vapor. So instead of calculating pressure from an equation, we usually look it up. And that is where steam tables come in. Steam tables are measured property tables for water. They tell us, for example, what pressure belongs to a certain temperature when liquid water and vapor coexist. So in this topic, looking up values is not a shortcut. It is the standard method. Now let's apply that idea immediately. Imagine we have a closed container with water and vapor inside. Then we cool the container down to 75 degrees Celsius. What is the pressure inside? The first step is not calculation. The first step is identification. If liquid water and vapor are both present, then the system is inside the dome. And once we know that, the logic becomes simple. Inside the dome, temperature determines pressure. So at 75 degrees Celsius, the pressure must be the saturation pressure at 75 degrees Celsius. Now we go to the steam tables and look up that value. For water at 75 degrees Celsius, the saturation pressure is approximately 38.6 kilopascals. That is about 0.386 bar. Now compare that with atmospheric pressure, which is about 1 bar. So the pressure inside the container is much lower than the pressure outside. That means the container has developed an underpressure or partial vacuum. And now we can also understand why. When the system cools down, some of the vapor condenses back into liquid. That means there are fewer vapor molecules left, so the pressure drops. But the important point is this: the pressure does not drop randomly. It drops to exactly the saturation pressure that belongs to the new temperature. And that is the whole idea of this video. The dome in the PV diagram is the liquid vapor region. Inside that region, liquid and vapor coexist. And inside that region, temperature fixes pressure. That is why we use steam tables. So the main takeaway is, inside the dome, pressure comes from saturation data, not from the ideal gas law.